Hello, my dear student. Welcome to EPG Pathshala. I am Anchal Srivastava from Department of Physics, Institute of Science, Banaras Hindu University. Today, we are going to discuss about the module carbon nanotube, their properties and application under the paper Nanoscience and Technology 2. After completing this module, the student will able to learn about understanding various properties of carbon nanotubes depending on its structure. You will also learn different potential application of carbon nanotube. You will able to understand the recent advancement in nanotube research. The strength and flexibility of carbon nanotubes makes them of potential use in controlling other nanoscale structures, which suggests they will have an important role in nanotechnology engineering. The highest tensile strength of an individual multi-walled carbon nanotube has been tested to be 63 gigapascal. Carbon nanotubes were found in Damascus steel from the 17th century, possibly helping to account for the legendary strength of sword made of it. Recently, several studies have highlighted the prospect of using carbon nanotube as a building block to fabricate three-dimensional microscopic all-carbon devices. Many researchers has reported a novel radical initiated thermal class linking method to fabricate macroscopic free-standing porous all-carbon scaffold using single and multi-walled carbon nanotube as a building blocks. These scaffold possesses macro and nanostructured pores, and the porosity can be tailored for a specific application. This 3D all-carbon scaffold architectures may be used for the fabrication of the next generation of energy storage, supercapacitors, field emission transistor, high performance catalyst, photovoltaics, and biomedical devices and implants. Large quantities of pure CNT can be made into a fiber filament by wet spinning method. The fiber is either directly spun from the synthesis pot or spun from pre-made dissolved CNTs. Individual fibers can be turned into a yarn. Apart from its strength and flexibility, the main advantage is making an electrically conducting yarn. The electronic property of individual CNT fiber, bundle of individual CNT, is governed by the two-dimensional structure of CNT. At room temperature, CNT fiber has a conductivity one order of magnitude higher than best electrical conductors. CNT-based yarn are suitable for applications in energy and electrochemical water treatments when coated with an ion exchange membrane. Also, CNT-based yarn could replace copper as a winding material. Many scientists have built a motor using CNT winding. The properties of carbon nanotubes, known as CNT. Carbon nanotubes possesses several unique properties and is being potentially used for various applications, which utilized full advantage of CNT's unique properties of aspect ratio, mechanical strength, electrical and thermal conductivity. Here, I have tabulated the various properties of CNT for convenience and also discussed the application. Let us see the properties of carbon nanotube. I have also added the properties of graphene and other materials which is close to that value of those properties. First is the density, which we have taken in gram centimeter cube. If we see the value of CNT is the average 1.33. The aluminium, which is another material, their density is 2.7 and graphene is slightly higher than 1. So this is a low density material which suggests a lightweight material. Let us talk about the strength. The strength can be confirmed by the modulus. Here the Young modulus of CNT is more than 1000 gigapascal. However, in case of steel, it is around 200 gigapascal only. So with low density and high Young modulus, this is a very lightweight and strong material. Tensile strength is also 45 in case of CNT, whereas in case of steel it is only 0.4. So these are the parameters which makes them lightweight and strong. Let us talk about charge mobility, which is the important parameter for any device to work faster. This value is around 10 to the power 5 in case of CNT. The unit is centimeter square per volt per second, and this is also very high in case of graphene. However, the most known silicon based device having this mobility around 1500 only. Let us talk the electrical conductivity. This electrical conductivity in Siemens per centimeter. This is around 5000 in case of CNT, and in pure silver it is quite high. So it is reasonable the electrical conductivity of CNT in Siemens per centimeter. Let us talk about the surface area. The specific surface area of CNT varies from 50 to 1315 meter square per gram. However, in case of graphite it is only 25. So this specific surface area is quite high in comparison to the graphite. This also have ease of functionalization. This also give the biocompatibility and electrochemical activity. So this is all points which is lead to good biosensor material. Similarly, if I talk about high surface area and other things, this can be useful for supercapacitor, battery application and drug delivery. And if I talk about charge mobility and electrical conductivity, this will lead to good transistor and electronic devices. And mechanical properties give a bioscaffold and a strong composite and all this thing which is suited for these properties. Let us now talk about the properties of carbon nanotube depends on their rolling direction. This is another new feature in carbon nanotube. By rolling this tube, they have formed different kind of tube known as armchair, zigzag and chiral tubes. And depending on this rolling, this property of CNT changes. A graphene sheet is rolled up to form CNT in such a way that two carbon atoms coincide. With the wrapping indicates N and M, which we have discussed in our earlier module, where N and M are integer and CNT can be uniquely defined and described. Since CNT is a rolled up sheet of graphene, an appropriate boundary condition is required to explore the band structure. If CNT can be considered as an finitely long cylinder, there are two wave vectors associated with it, and the wave vector parallel to CNT that is continuous in nature due to infinitely long length of CNT, and the perpendicular wave vector that is along the circumference of CNT. These two wave vectors must satisfy a periodic boundary condition, and the wave function repeats itself. It is rotated 2 pi around CNT, and in this way the properties of nanotube will change, which is discussed in our next slide. There has been considerable practical interest in conductivity of CNT. CNT with particular combination of N and M, the structure parameter indicating how much the nanotube is twisted, can be highly conducting and hence can be said to be metallic. Their conductivity have been shown to be a function of their chirality, degree of twisting, as well as their diameter. CNT can be either metallic or semiconducting in their electrical behavior. Conductivity in a multi-valve nanotube is quite complex. Some types of armchair structure CNT appear to be conduct better than other metallic CNT. Furthermore, interval reaction with MWCNTs have been found to redistribute the current over individual tube non-uniformly. However, there is no charge in current across different part of metallic single-valve CNT. The behavior of rope of semiconducting SWNT is different in that of the transport current changes abruptly at various positions on CNT. Based on the chirality and the integers N and M, the electronic band structure has been calculated, theoretical calculation has been made, and it has been found that electronic structure is determined by following. If N is equal to M, the nanotubes is of the kind which is known as metal. If N minus M is 3J, where J is non-zero integer, a tiny band gap will open in CNT. Otherwise, on other cases, large band gap semiconductor. So the important thing is that with the same material, it can be metallic depending on N-M values and the diameter, or semiconductor with different band gap. For example, 7,7 nanotube where N is equal to M is metallic in nature, and a small band gap semiconductor can be shown in case of 6,0 nanotube, and large band gap semiconductor may be 7,0 and things like that. So band gap, as I discussed you, is depend on M and N values as well as the tube diameter, and depending on the tube diameter, which is definitely depends on N and M value, the band gap changes with these conditions. Now let us discuss the mechanical properties of carbon nanotubes. In carbon nanotube, sigma bonding is the strongest in nature, and thus a nanotube that is structured with all sigma bonding is regarded as an ultimate fiber with the strength in its tube axis. Both experiment measurements and theoretical calculations agrees that a nanotube is a stiff as are stiffer than diamond and the highest Young modulus and tensile strength. Most theoretical calculations are carried out for perfect structures and give very consistent results. For 1010 single watt carbon nanotube and bundle of MWNT with comparison with other materials. The table in slide summarize calculated Young modulus, tube axis elastic constant and tensile strength for is it an agreement with the experiments on average. Experiment results show broad discrepancy especially for multi-valve nanotube because multi-valve nanotube contain different amount of defects for different growth approaches. We have many methods to grow MWCNT and depending on the temperature and other parameters, the amount of defects are varies and therefore the properties of MWCNT varies from growth to growth method. In general, various type of defects free nanotubes are stronger than graphite. This is mainly because the axial components of sigma bonding is greatly increased when graphite sheet is rolled over to form a seamless cylinder structure of SWNT. Young modulus is independent of tube chirality but depends on the tube diameter. Experimental study for calculating mechanical strength of CNT has been shown in figure. The highest value is from tube diameter between 1 and 2 nanometer, about 1 terapascal, whereas in case of steel it is only 200 gigapascal. Large tube is approaching graphite and a smaller one is less mechanically stable. When different diameter of SWNT consist in a coaxial MWNTs, the Young modulus will take the highest value of SWNT plus the contribution from the coaxial intertube coupling or van der Waals forces. Thus, the Young modulus of MWCNT is higher than SWNT, typically 1.1 to 1.3 terapascal, as determined by experimentally and theoretically. On the other hand, when many SWNTs are held together in a bundle or a rope, the weak van der Waals forces introduce in a strong shearing among the packed SWNT. This does not increase but decrease the Young modulus. It is shown experimentally that the Young modulus decreases from 1 terapascal to 100 gigapascal when the diameter of SWNT bundle increases from 3 nanometer, about 10 SWNT to 20 nanometer. Let us discuss the thermal properties of carbon nanotubes. CNT can exhibit superconductivity below 20 K, approximately at minus 253 degrees Celsius, due to the strong in-plane carbon-carbon bond of graphene. The strong CC bond provides the exceptional strength and stiffness against axial strains. Moreover, the larger inner plane and zero in-plane thermal expansion of SWNT results in high flexibility against non-axial strains. Thermal conductivity has been found around 3000 watt per millikelvin in an axial direction with a small value in the radial direction or insulator shown in figure. Due to their high thermal conductivity and large in-plane expansion, CNT exhibit exciting prospect in nanoscale molecular electronics, sensing and actuating devices, reinforcing additional fiber in functional composite material, etc. Recent experimental measurements suggest that the CNT embedded matrix are stronger in comparison to the bare polymer matrix. Therefore, it is expected that the nanotube may be significantly improve the thermomechanical and the thermal properties of the composite material. Let us discuss CNT application as charge storage material. CNT have the intrinsic characteristics desired in material used as electrode in batteries and capacitor. Two technology of rapidly increasing importance. Here is the figure suggesting lithium-ion battery where lithium ion can be stored inside nanotube. Similarly with capacitors. CNT have a tremendously high surface area, around 1000 meter square per gram. Good electrical conductivity and very importantly their linear geometry makes their surface highly accessible to the electrolyte. Research has been shown that CNT have the highest reversible capacity of any carbon material for use in lithium-ion battery, which is shown in figure. In addition, CNT are outstanding material for supercapacitor electrode and are now being marketed for this application. CNT also have application in a variety of fuel cell components. They have a number of properties including high surface area and thermal conductivity which makes them useful as an electrode catalyst support in PEM fuel cell, which is proton exchange membrane fuel cell. They may also be useful in gas diffusion layers as well as current collectors because of their high electrical conductivity. CNT high strength and toughness to weight characteristics may also prove valuable as a part of composite components in fuel cell that are developed in transport application where durability is extremely important. Let us discuss the application in field emitters. Field emission results from the tunneling of electron from a metal tip into vacuum under application of a strong electric field. The small diameter and the high aspect ratio of CNT is very favorable for field emission. Even for moderate voltage, a strong electric field develops at free end and supported CNTs because of their sharpness. This was observed by D. Heer and co-workers at EPFL in 1995. He also immediately realized that this field emitters must be superior on conventional electron source and might find their way into all kind of application. Most importantly, flat panel display. It is remarkable that after only 5 years, Samsung actually realized a very bright color display, which will be shortly commercialized using this technology. Field emission property of CNT has been shown in the figure. Let us discuss the nanotransistors based on CNT. On the keys of being able to reduce the transistor to such a small size is the use of carbon nanotube as the channel is placed on silicon. The nanotube is only 1 nanometer thick. Such thickness offers a significant advantage in electrostatic so that it is possible to reduce the device gate length to 10 nanometer without seeing the device performance adversely affected by short channel effect. An additional benefit of nanotube is that the electron travel much faster, which contributes to the higher level of device performance. Another key contributors to the small scale of transistor is adoption of end-bounded contact. The metal contact in transistors have typically been bonded lengthwise along the main body of the transistor semiconductor material, resulting in a long contact along the channel. 2 years ago, IBM demonstrated that this end bond configuration made it possible to shrink the contact length of experimental nanotube transistor from 300 nanometer to just 10 nanometer without any increase in the contact resistance. CNT as channel material has been shown in figure, and its result has been shown with varying gate and biasing voltage. Let us discuss the CNT's application as filters. Photograph of arrangement used for heavy hydrocarbon separation, and schematic of the petroleum dynamics through the bulk tube, and GC spectrum of unfiltered product. GC spectrum of a sample after it was passed through the nanotube filter, showing the absence of heavier hydrocarbon. So this is the example. Filtration of a special kind of tube which is made up of carbon nanotube has been shown in this photograph. This also removes the bacteria from this nanotube filter. The unfiltered water containing E. coli bacteria has shown in the figure. The colony of E. coli bacteria marked by arrow grown by the culture of the polluted water, and the assembly of the filter assembly in C has been shown. In D, the water filtered through the nanotube micropore and the filtered after culture using the absence of bacterial colony. So these are the two examples of showing CNT as work as a filter, where one can filter the higher hydrocarbon as well as bacteria and viruses from the system. Let us talk the miscellaneous application of carbon nanotube. Worldwide, commercial interest in carbon nanotube is reflected in a production capacity that presently exceeds several thousand tons per year. Currently, bulk CNT powder are incorporated in diverse commercial products ranging from rechargeable battery, automobile parts, sporting goods to boat hulls and water filters. Advances in CNT synthesis, purification, and chemical modification are enabling integration of CNT in thin film electronics and large area coating, although not yet providing compelling mechanical strength or electrical or thermal conductivities for many applications. CNT yarns and sheets already have promising performance for application including supercapacitor, actuator, and lightweight electromagnetic shielding. Various application of CNT includes CNT quantum wire interconnects, diode and transistor for computing, data storage memory, capacitors, field emitters for instrumentation, flat panel display as a sensor, biosensor, NEM CNT based microscopy, AFM tip, etc. Nanotubes can be also used for sensing in bio and chemical sensing, batteries of lithium-ion battery, fuel cell, nanoscale reactors, ion channel, biomedical application, nanoelectrodes for implantation, artificial muscles, and many more. So students, let us now summarize what we have learned in this module. CNT possesses several unique properties such as high Young modulus, around 103 gigapascal, excellent electrical conductivity, around 106 Siemens per centimeter, high charge mobility, which is the order of 10 to the power 5 centimeter square per Vs volt second. CNT provides high specific surface area and ease in functionalization for biosensing application. Properties of CNT depends on rolling direction. CNT are thermally conducting along the axis and insulating along the radial direction. CNT are being potentially used in several fields: are biosensing, energy storage, capacitor, nanotransistor, filter, and many more. So this all we learned in this module. Thank you.